And we're going to move right along to our next session with Jonas Bonér, Transcending the Barriers to Elasticity, which is sponsored by Akka. Jonas is the inventor of Akka and the CTO and co-founder of Lightbend. He's a distributed systems innovator and OSS community leader. He wrote the very influential Reactive Manifesto and Reactive Principles and numerous design books that set the foundations for how we tend to think about and build systems today. The Reactive Manifesto in particular really was an eye-opener for a lot of architects about the way to think about systems. Jonas is the originator of Akka, the flagship solution from Lightbend for building, operating, and securing distributed applications. He's also an amateur jazz musician and a passionate skier who holds a Bachelor of Science from Mid-Sweden University. So please welcome me in joining Jonas.
Thanks a lot, Neil. Yes, I'm going to talk about elasticity here and how we, as developers, could help sort of transcending the barriers to elasticity, because there are many. To free up the infrastructure to do what is best, by doing, by sort of leveraging good principles up in the application stack. So, but let's start with some definitions. What does really elastic mean? Merriam-Webster defines it as being capable of ready change or easy expansion and contraction. And I'd say that my definition is that it's a system that stays responsive under any external factor, workload, operations, failures, by scaling up or down on demand. So sort of being able to react. It's really being able to react to changes by sort of increasing or decreasing resources allocated to service, the inputs that are arriving into the system, and sort of allow the application to be sort of stretched out or contracted in a transparent fashion as a reaction, to these changes of inputs. And most people talk about, elasticity to be able to really handle workload, and that's what or sort of changes in workload, and that's of course very, very important. Being able to scale up or down compute, scale in and out servers, scale data, and address sort of variations in workload in general. But I also think that it's quite important to think about ops here as well. How can we make it easier for operations to rebalance and repartition workloads, to enable sort of upgrades without any downtime, schema changes and maintenance events and so on. And that sort of ties very much also into elasticity. And of course, failure as well, being able to recover, move, and replicate workloads, as a sort of response to failure, hardware failure, network failures, or system failures. So with that little bit of sort of broader definition in mind, let's dive into some of the barriers to elasticity. First, I want to say that I don't think that elastic cloud infrastructure really translates to application elasticity. I see them as two different things that need to work in tandem. And as developers, we can, there are many barriers that we can run into, and unless we think ahead, we as developers and also operations staff, might be forced to rethink and rewrite application to sort of transcend each one of these barriers. The first one, this of course is very, very high level because I only have 30 minutes. So the first thing to watch out for is compute saturation, meaning sort of I/O being sort of compute bound. That usually means very poor resource utilization, and it's often due to sort of contention on shared state. The second sort of barrier that many run into is I/O saturation. It's often due to her blocking I/O and synchronous messaging, synchronous RPC, and so on between services and nodes and so on. And it's partly what also drives database saturation. And it's unfortunate that we often see sort of many high compute applications are idling because the database is saturated. The third thing to watch out for is what I named here connection saturation. It might not be the best name, but what I mean here is like that where you end up in a situation where you exhaust the connection pool. More compute nodes actually doesn't help. They yield diminishing returns because there's too much contention on the single sort of database or resource that you would like to connect to, and that might make it hard to know when should you scale up or rather scale out and scale in and stuff like that. And finally, how do we handle disaster recovery? We we need to start thinking about things like region to region replication, stretching out the application up into multi-region, sometimes onto multi-cloud as well, and manage the RTO, the recovery time, which if not done correctly can be quite high. And of course, as you move the application, stretch it out across different geographic regions, we need to think hard about security and regulations, compliance, and all of those things. So the thing is that like most problems in distributed systems revolve around how we manage distributed data. And database replication, it really imposes a lot of application and app or an ops limits. And the most common approach is to distribute the database. And there are sort of three different archetypes, if we should be high level, to this. The first one is physical replication of sort of binary data down at the infrastructure level. This low level, sort of a black box, is a little bit inflexible, sort of a brute force approach, and can be hard to do, like things like rolling upgrades and so on. The second thing, or the second archetype, is logical replication. That is done at the database level, and here you sort of replicate the DML, the data modification language, and one of the problems here is that since we don't have a DDL replicated, we can't really replicate schema changes like views, large object sequences, foreign table, and stuff like that. So that leaves us with schema replication, which sometimes can be hard to operate, honestly, and it sometimes has a tendency to modify application behavior. It's not completely transparent. It can lead to consistency conflicts and so on. So in my experience, it's better to think about not distributing the database per se, low level down at the infrastructure level, but instead, think how we write the application and write it in a way that we can distribute the data itself up in the application tier. And if we do this, correctly, I'll talk a little bit about it. I don't have that much time, but I'll talk a little bit about it. It's like then we can let the in-memory state, your actual domain model, your state in the actual microservices, be the source of truth. And then you end up with a model that is where state replication and state persistence is actually application and domain aware. So you don't need to map your in-memory state down to the actual database. Instead, you can use any data structure, it also makes it fairly easy to divide and conquer. Working with smaller data sets that leads to less contention and so on, and allows things like efficient sharding or replication. And as I will talk about, managing state, in this way, or persistence in this way up in the app tier means that we can get lots lower latency because the data is right there in your application instead of you need to do another network hop down to the database and all this, go and fetch the state. And when you're done with it, you always need to store it back into the database. So it also helps, I think with migrations, stuff like that, because everything you have, is up in the app tier, under the developer's fingers, and there's not any mapping have to do down to the database below. And in practice, sort of a foundational sort of tool or pattern here is use event-driven architecture. That gets us a long way. Alongside things like event sourcing and so on. I don't have enough time to talk about these in detail here, but I'm just hinting at them. So, the biggest enemy of elasticity is contention, and we really need to work hard at minimizing contention. And when I say contention, I mean access, so parallel access to shared resources in the system. It's really contention that kills scalability and also kills performance. And being able to be then asynchronous and non-blocking, using non-blocking, I/O and so on, that sort of gives the caller the option to be able to perform other work asynchronously rather than being sort of blocked and waiting for resources to become available. So queue up sort of wait time and add wait time to the system. And that means that we can be a lot more efficient in how we use resources. We can be more cost efficient, being more energy efficient. And in practice, it means, it can be achieved by allowing the caller to simply put a request on the queue and register a callback. To be notified later when the result is available, and then return immediately after doing so, and sort of freeing up the thread or the resources to be used by others and continue execution, and then be called asynchronously when the result arrives. Also, things like data partitioning is extremely important here. Being able to partition your data into smaller data sets for minimizing contention, and also not really sharing mutable state, freely, because as soon as you do that, you need to introduce locks and wait times and queues and stuff like that. Instead, share immutable facts. I'm going to get more into that later. It's really, it really needs to be async and non-blocking all the way down. So it's really the weakest link in the chain that matters. And there's two concepts that are really important here to be aware of. First, we have contention. That can be defined as the wait time, waiting or queuing for shared resources. The second thing that is also, is important at play here is what is called coherency. And that is sort of the delay for data to become consistent. And we have Amdahl's law that talks about contention, how contention affects the parallel system and how contention can sort of give diminishing returns as you add as you sort of try to scale up the system. As you can see here, that the more it very, very hard hits on how much speed up we have, on the vertical axis, depending on how much sort of parallelization we have in the system as we scale it out. But that's not the end of the story. We also have the universal scalability law, which in a way sort of builds on Amdahl's law by adding coherency. And as I said, coherency can give negative results. What we really want to achieve here is linear scalability. That's the sort of the straight line there. Amdahl's law, as I said, as contention. But if you don't take coherency into account, or incoherency into account, then you might miss that is actually, as you add resources to the system, more nodes, more cores, you can actually get negative results. So this is something to really be aware of. So I really think this, on a fundamental level, systems need to be decoupled. I think we all can agree with that, and they need to be decoupled, in time. That's, decoupling systems in time is really what gives us concurrency. It adds sort of an asynchronous boundary and gives us loose coupling. But we also need to decouple the systems in space. And decoupling in space is what gives us distribution. Is be able to communicate across context, across cores, across nodes, across data centers, clouds, etc. And these things really can provide the foundation for resiliency, for mobility, and for elasticity. This might be a contentious one, but I'm a firm believer that strong consistency is the wrong default in distributed systems. We often use strong consistency just out of habit, in inertia. It's how we've always done things. But it really adds a lot of contention. It adds wait time. It's often too brittle, and it's really hard to make available. It's hard to make resilient. As Pat Helen, have said numerous times, these are actually two quotes from two different papers. He said that the developers simply do not implement large scalable applications assuming distributed transactions. two-phase commit is the anti-availability protocol. And when you think about it, it's not really anything to be surprised about, because it's not really how the world works. The world is inherently eventually consistent, with causality at play. And pretending that everything is strongly consistent, can sometimes make things worse, even though it is a very great developer convenience. It is a leaky abstraction. Don't get me wrong, there's nothing wrong with strong consistency. Where it works is like magic. It removes so many sort of problems for us. But I think it's a wrong default, and it should be used like carefully and deliberately where you absolutely need it. So to sum things up, don't carry around more guarantees than you need. Since every guarantee that you add to your system has a price. It has a price in terms of scalability, in terms of resilience, reliability, availability, maintainability, and so on. So I think it's better to start with the weakest guarantees possible, and then analyze the system, and then think, okay, where do I need to layer in stronger guarantees, and do it in those places, not just as a wet blanket across your whole system, so to speak. The truth is actually that a distributed system is really a never-ending stream towards convergence. It's always in the process of convergence, but it never ever reaches the state, as in final state of convergence. So we can assume that we will never ever reach it. If we do, it's usually just for brief moments in time, and then it's back to the process of convergence. So the system in a distributed system is really constantly in motion. It's constantly in a state of change. It's always trying to catch up to whatever happens over there or over there. And there's really no now. It's really no globally consistent now. No globally consistent present. As the expression goes, it's all in the eye of the beholder. Present and now is really subjective. So what I think we need to do is we need to think in terms of consistency boundaries and decompose the system into these small islands of strong consistency, in sort of a river of constant change and uncertainty. And how do we do that then? How can we then craft sort of these autonomous islands of determinism and strong consistency in this sort of river of uncertainty? If we're able to do that, we can actually live happily forever, under the illusion that time is absolute, that there is a single present, there is a single now, and that the world is deterministic, because we boxed that into this island within our consistency boundary. We can really have this atomic view on the state, but it requires that we own our data exclusively. Each service, each component, whatever you treat as your consistency boundary, really need to own its data exclusively. And to model this, we can work with bounded context, microservices, of course. Entities is usually the best way to model these things, and they map very well to actors. That I've been using for a decade now for these type of things. And the thing is that if we then are able to craft these units of consistency between them, we have to rely on eventual consistency. And don't be surprised. It's really how the world works. As I said, I don't think we should fight reality. We should embrace it, and that can liberate ourselves in how we design systems better. And Pat Helen defines this really nice conceptual model for how to think about this, how to think about consistency in a distributed system. He talks about inside data as our current present, our current local present. That's our state. That's the state we have inside our consistency boundary. Then we have outside data that he calls blast from the past. That's our facts, arriving as events into our system, and that we are emitting out to the world. If you're able to do that, you can really work with values between these consistency boundaries, which gives other components, a really good solid foundation for reasoning about what's going on, because immutability, is the name of the game there. Facts don't change. And between services, he calls that hope for the future. This is almost poetic in a way. That's our commands and requests. That's someone asking someone else to do something. So why does he call it hope? I think it's really around that. There's no promises here. Commands and requests, they can get dropped. Content can get garbled on the network. They can even be rejected by the receiver because they're invalid or whatever. So shared state, shared mutable state, as I talked about, is unfortunately still the norm. And the reason why it's problematic is that updating place can really get us into trouble, especially if this mutable state is globally shared, because it needs to be guarded and so on. And things you can receive an object and you look at it and it's one value, and the next second is another one. It's really hard to do reasoning on this on such a fragile foundation. So and it leads to really increased contention, coordination, wait time, and so on. So I really think that we need to contain mutable state, and the best way to think about it is that we need to make it non-observable to the rest of the world. Fully contained in this safe haven, of strong consistency, but only used for local computations. So when you're done with your processing, then using mutable state in your business logic in your component, and you're ready to tell the world about the results, then we can take the result, we create an immutable value based on that, and then we publish that as a fact for the outside world to act upon, or we feel if we store it to an event log, for example, then you have a full the full history of all the state changes that ever happened to that component in order, so it can be replayed. It can be replayed for replication, for failure, recovery, and so on. And as I said, one of the best things with this is that then others can base reasoning on stable values that simply don't just change. And good tools for this, as I said, is like actors, entities, event-driven architecture, event sourcing, CQRS, and so on. Another very important, piece in the puzzle is location transparency, and async message passing. In my opinion, in my sort of experience, it gives us one communication abstraction across all dimensions of scale. And what I mean by that, we have one sort of programming model, one way of doing communication with unified semantics, regardless how the system is currently deployed, regardless of which topology it currently has, which actually can change. So instead of relying on different tools and semantics for different levels of scale, meaning if we're working core to core or container to container, server to server, data center to data center, we can like, for example, using callbacks for a single core, for example. Or use threads and locks across core. So we use messaging or some pub sub across cores and data center. Instead, we can if we use async message passing, we get location transparency as a unifier of all of these sort of dimensions of scale, from core to socket to CPU to container to server to rack to data center to region, global. It all looks and feels and behaves the same according to the same semantics. So another really important thing is that we really need to distribute data and logic together. And here I'm going to talk a little bit our experiences, designing Akka as sort of a template, how it all can be put together. So lessons learned from thousands of users that we've been helping. So there are sort of three important principles here that you should always bundle state and logic. So sort of state should be embedded sort of in the application, sort of in a sort of in-memory database. And that sounds more overkill than it is, because these right patterns like event sourcing and so on can really give you that. The benefit of this is like the application then is a system of record, not the database. And you distribute the data and not the database. And these things map. If you have logic and state fully coupled, or bundled together. It maps very well to actors, to microservices, and so on. And one of the really good things is that you can run it anywhere, since it's exposed to the world through location transparency. It can actually be moved out, to the end users running in the cloud, or even out at the edge for extremely low latency. And you get sort of resilience almost built in, because if you move the component out to the outside, to the furthest out edge, you can actually lose the connection to the back-end cloud and still continue to function as nothing happened, because you have the state, you have the processing, and you have the user that you want to serve right at the same physical location. Then as if the connection to the back-end cloud is restored, you can just start making use of that for backup propagation, for communicating with peers, for replication and stuff like that. The other thing is that I found really important is, like, no node should really be special. They should all be masterless peer-to-peer communication, and every node really needs to be able to serve both reads and writes. That eliminates bottleneck and performance degradation as you scale this system out. And finally, being able to have sort of masterless cloud-to-cloud replication. Being able to have a system that is where you have homogeneous execution across heterogeneous locations. Being able to scale replicas, across all these dimensions of scale that I talked about. And we provide the backbone for that with Akka sort of distributed data mesh that sits right underneath your application above the infrastructure and doing all the magic. So how are we implementing this? Yeah, a few important patterns here is like data sharding, for example. Each service here is sort of clustered from within. We have sort of and sort of forming like a node ring using epidemic gossiping. And this means that nodes can join and leave as needed for truly transparent scalability. And we use consistent hashing here to sort of spread out all the data across buckets in each one of these nodes. And if there's a miss, request miss, then we sort of do auto routing to the correct instance. Another very, very important thing is that since node can come and go, and sort of this node ring can sort of grow and shrink, it's extremely important to be able to do data rebalancing, be able to sort of rebalance the data across all the current available nodes. And finally, a very important thing is also that we separate like queries from writes, meaning reads from writes. This means that we can that the system can write fully uncontended, down to the event log, storing all the events in the system, really employing the single writer principle, and then we can scale the reads, separately from the writes. This is really important because sometimes you have a write mostly system and sometimes you have a read mostly system, and bundling it all together into one single database can make it hard to optimize your resources. And it also, like as a nice side effect of this, it also supports multiple query models, since all the changes are then replicated over to the query side on the side. That means that you can have multiple subscribers to that to those change sets, so to speak, to these facts flowing. And in practice, you can have a graph database. You might want to put things into Postgres for backoffs. You might want to push things into Spark for more thorough processing and so on. And they can all run in parallel, without really affecting the right side at all. This pattern is called CQRS, and is something that is quite useful. I think ops elasticity is also equally important to workload as elasticity, as I talked about in the beginning. Being able to have ops, migrate and upgrade without downtime, and to support this, we have three different replication schemes in Akka. We have sort of pinned for ensuring data sovereignty. We have multiplace with replicated read for global HA, that's sort of active passive. And we have multiplace replicated write for like really continuous WAN-based replication, where all replicas are fully active, serving both reads and writes. And these different models really means that that ops can get a lot of flexibility of managing the application without any downtime. Changing the application, the data, changing the topology, even moving from single region to multi-region. Things like version and schema changes and so on, and even update the underlying infrastructure, because that's completely decoupled from how the application is doing all of this. So to sum things up, using these principles, Akka's really been able to support elasticity completely transparently across this whole application stack. Like from bottom up, scaling compute up and down. We usually like actors and streaming for the stuff like that. Scaling data, automatic rebalancing and replication of data using things like event sourcing, streaming projections, like sort of materialized views. On the app level, we have sort of masterless clustering, as I talked about, with completely, all replicas really being able to serve those writes and reads. And on the network level, being able to stretch these out geographically, across regions, across multi-cloud, all provided, by this data fabric and this sort of single unified programming model that can really help you scale across all these abstractions. So there's some stats there, as well. I'm not going to go into those, but I just want to, close with, these design principles that I just talked about can really, in my experience, give you a ton for your work. Really yield amazing work. Really yield amazing results. Things like removing all the barriers to elasticity. Shock-proof resilience and easy way to manage data and cloud sovereignty. That many needs now with GDPR and other things. And really being able to serve your clients with the shortest response time. With the highest throughput.